Welcome to the world of InSitu visualization. The word InSitu means the real-time visualization, on-site, in place, and exclusive. Let's understand this concept with a real-life example. Here is a running turbine and a bulb. We are directly supplying the generated electricity to the bulb without storing it to lighten up the bulb. To understand this art of InSitu visualization in the world of simulations, we can see here the simulation codes, and here is the output visualizations. We are using one of the most popular software called Paraview and its most beautiful feature called Paraview Catalyst. Let's see some of the Paraview Catalyst examples. Fortran code, Fortran adapter, and C++ adapter, and the Python pipeline, which connects to the Catalyst in the visualization node. This is how it works. The whole simulation is working on the simulation nodes and visualization is working on the visualization node. This is how the Paraview Catalyst works. Without storing the data, just directly transferring the data. This is something exclusive. Initially, I was thinking I'm going to see the real tornado movements. But here we are simulating the evolutions of the 3D vector field having the validity of the entropy and energy formulas, which are used in our main simulation code. I was trying to understand the main simulation code so that I can write the adapter function for the required parameters, but I was totally confused. So I had a long discussion on Skype call with my mentor. After the discussion, I found the right place where I can instrument the adapter functions for the required parameters. Let's try to understand the overall configuration of the programming code. We have one input file with the domain configuration, starting time, and the Gaussian center, which belongs to the Fortran main simulation code in which I instrumented the adapter functions, which calls the Fortran adapter having a data pipeline, from where I transfer the data to the C++ adapter so that we can convert it into the VTK image data, which Paraview can understand and display, which connects with the Python script having lot of filters in it, which invokes the catalyst in the visualization node inside Paraview for the live visualization. Test run of beta version 1.0 with small domain size using one node with 16 cores. Let's see the results. As you can see here, the velocity field, which looks like donut, is not increasing along the z-axis because the energy with this domain size is decreasing linearly and analogously with respect to the entropy. We had discussion of what we can do with domain size. As the domain size is too small, we have decided to take a big domain size of 121 x 121 x 1048 as my mentor used once. But another problem was he used 4000 cores to run the simulations, which is almost 35% of the big supercomputer, which was practically impossible for us now. So we have decided to reduce the box size to 121 x 121 x 548, and from our calculations it should run nearly by 64 cores. Final run of the beta version 1.7 with the decided dimensions, and here we used 4 nodes with 16 core each to run our simulation. We are trying to simulate the infinite system and to look on appropriate finite region, and let's see how the Paraview Catalyst works with simulation codes. Let's open our Paraview Catalyst on the visualization node and try to connect with the Catalyst on the receiving node. So here you can see we pause the simulation on the current time step to see and to extract the input. Here you can see our domain size. This means we assume that at every time step we have the velocity outside the domain which is equals to 0, which implies our simulation is adequate to the true system only. Let's discuss the final results. Here the energy is increasing from 100 to 150. This means that there is increase in the velocity along the z direction. So we have defined our Gaussian center at 20 along z-axis. It means we can see there is non-zero velocity after every 20 steps in between and is enlarging, which looks like donuts. When these donuts are reaching the boundary of the domain size, this means that the velocity values at the boundary is different from 0, which contradicts our assumption at this time step, which means we have to look only before that time step. If we see the entropy at every point which is changing with the time, more precisely where the velocity is not equal to 0. So this is true for every finite region. We can only reach near the explosion time. Of course, more large the region, more big the evolution time. But in any case, we can't arrive at the explosion time with any region. Thank you.